Hello, Math 1316 Trig students. Again, I'm making a video to make up for this yesterday's bad Cisco WebEx transmission, and hopefully as backup for in case tomorrow's Thursday's Cisco WebEx is also equally bad. Since I haven't received any help for fixing that, I'm sort of taking matters into my own hands here. I am going to be sending you announcements about how there are a lot of videos on the playlist for pre-calculus that cover the essentials of trigonometry. One of them is called it's in Math 2412, this pre-calculus playlist. One of them is called the co-function identities. And really, I think it could be a little more brief. So I'm adding this second video to your Math 1316 playlist to kind of redo that part. So where did this phrase cosine come from? By the cosine of theta, what actually they meant by that was the sine of the complement of theta. So remember, if theta is here in standard position, and it's an acute angle less than pi over 2, then its complement here, theta prime, is also an acute angle. And whereas we usually refer to the cosine of theta as being the x-coordinate of piece of theta in our class. In the first quadrant, that means it's the length of OQ. The length is the same thing as that trig function value. And also the sine of theta, because it's the second coordinate and our angle is terminating in the first quadrant, the sine of theta is the same thing as the length of the side P to Q. Okay, that's all very fine and good. What do people mean when they're talking about the cosine of theta originally? What they were talking about is, if you look over here in this other right triangle, OPV, so I have projected on P onto the y-axis here, and I get V at its foot. In this POV, this point of view triangle here, theta prime is this angle in here, and the sine, or the length of the side opposite it, would be P to V, right? So the sine of theta complement, the sine of the complement of theta, the sine of pi over 2 minus theta, or the sine of theta prime, they all are the same thing as what people refer to as the cosine of theta, which you can see makes sense because OQPV forms a rectangle. If we take the picture of this rectangle out and enlarge it, right, you can see the length of the side OQ, which up here is cosine of theta. If I label that here, the side opposite in the triangle POV, the side opposite theta prime, is called its sine. So the sine of theta complement is the same length as cosine of theta. Saying the sine of theta complement is the same thing as saying the sine of the complement of theta, or arithmetically, in numbers, the complement of theta is pi over 2 minus theta. So the sine of pi over 2 minus theta is equal to the cosine of theta. In the same kind of way, looking at theta prime, it has the side adjacent to it is called the cosine of that angle, just like over here. Well, we came from the habit of seeing that this side here is the side adjacent to the angle theta. So the side adjacent to theta prime is the cosine of theta prime. And that, it turns out, is exactly the same as the length of the sine of theta. So we have our second co-function identity here. Another thing that a bit of a fundamental trig identity that I didn't get to in the first video on fundamental trig identities is I meant to talk about the symmetries. The symmetries, even or odd symmetries of the trig functions. If you recall in college algebra, you talked about functions that were even, like y equal to x cubed. Excuse me, y equal to x squared. That's an even one. It's the power function whose exponent is an even number. So it helps you realize why they call this even. Notice how that's symmetric about the y-axis versus y equal to x cubed was said to be symmetric about the origin, okay? Because if you took f of the opposite of x, that was equal to the opposite of f of x. Whereas over here, that's for an odd symmetry. If it's an even symmetry, then we have the property that f of the opposite of x is the same as f of x. So that's where those even symmetry, odd symmetry designations are coming from. Power functions with odd exponents have an odd symmetry or satisfy this property. Power functions with an even exponent satisfy this property. So, well, as it turns out, the sine and cosine have some symmetries. And let's look at this picture to see why. If I compare an angle theta with its opposite, if I am assuming theta is positive, I'm going to draw it in the counterclockwise direction. So the opposite of theta I would draw in the clockwise direction. My claim is that these two triangles are similar, right? So this one's p sub theta here. This is q sub theta. But on the other hand, this is the point p sub theta prime, p sub opposite of theta, not prime, but the opposite of theta. And, well, if you project up to the x-axis, that point is also called q sub opposite of theta. So the links from O to Q or O to Q, the opposite of Q, they're exactly the same. Another way of looking at it is the points p sub theta with coordinates cosine theta, sine theta, and p sub opposite of theta with coordinates cosine of the opposite of theta, sine of the opposite of theta. Those are on the same vertical line. You could say the equation of that vertical line is that x is equal to the cosine of theta. But similarly, you could say it's equal to the cosine of the opposite of theta. Oh, so these two things are equal. Right? So therefore, the cosine of the opposite of an angle is equal to the cosine of that angle. We say that the cosine function is even. For sine, it's opposite in sine. So here's the second coordinate here is the sine of theta. If you buy that these two triangles are similar, then the length of this segment right here must be equal to the length of that segment there. Mind you, the coordinates of this point, because we're in quadrant 4, would not be equal to this length, but it's opposite. So if this length is actually the sine of theta, the y-coordinate of that point is the opposite of the sine of theta. So therefore, the sine of the opposite of theta, that's what we call the y-coordinate of p sub opposite of theta, turns out to be equal to the opposite of just the sine of theta. And that gives us this odd symmetry about the sine function. So the cosine function is even. It's acting like an even function. And the sine function is odd. If you go into the other 4 basic trig functions, using these, you can prove that the tangent, which is a sine over a cosine, the tangent of the opposite of an angle is the opposite of the tangent. Same thing is going to be true of the cotangent, because it's a cosine over a sine. Secant is just 1 over the cosine. So the cosine being even makes the secant even. The cosecant is just 1 over the sine. So because the sine is odd, it's going to turn out that the cosecant is odd as well. So of the 6 basic trig functions, we have 1 and 2 that are even, the cosine and the secant, and everybody else is odd. All right, so this ends the second video in the series about trig identities. After this, I'm going to direct you to look at the Math 24-12, which is the pre-calculus class. Its videos on all those other identities are pretty good. So that's where I'm going to have you go to see those, the material that I would cover in class if we had good transmission. All right.